Today, in this short introduction to practical crystallography, we're going to cover a brief history of X-ray crystallography, we're going to review chemical bonding, and we're going to follow a student as she completes a single crystal X-ray experiment using the mineral pyrite, commonly known as fool's gold. So, let's begin. Have you ever wondered how scientists were able to generate images of molecules such as this one, and this one? These molecular models, known as ORTEPs, short for Oak Ridge Thermal Ellipsoid Plots, were first generated in 1965 at the Oak Ridge National Laboratory in Oak Ridge, Tennessee. They quickly became the favorite of X-ray crystallographers trying to determine the structure of complex molecules. But what exactly is X-ray crystallography, and how does it work? To examine this question, we need to look back a further 50 years in time to two very remarkable scientists from England. In the years leading up to World War I, William Henry Bragg, then a professor of physics at the University of Leeds, and his son William Lawrence Bragg, a research student at the University of Cambridge, began a series of experiments that would ultimately win them the 1915 Nobel Prize in Physics. Building on Max von Laue's discovery that passing X-rays through a crystalline structure results in a highly ordered diffraction pattern, the Braggs determined that if the wavelength of the X-rays and the angle of incidence were known, it was possible to use the diffraction pattern to determine the structure of crystals. This technique, known as single crystal X-ray diffraction, has since been used to determine the structure and chemical composition of many solid-state substances. For example, X-ray crystallography was famously used by another English scientist, Rosalind Franklin, who, along with her research group in 1952, took this mysterious image of DNA, known as Photo 51. The following year, scientists Jim Watson and Francis Crick would use Franklin's image to help determine the double helix structure of DNA, though they would not popularize her contributions. They would later go on to win the 1962 Nobel Prize in Physiology or Medicine for their discovery. Franklin, however, had tragically died at the age of 37 in 1958 and was not nominated for the award. Today, X-ray diffraction is one of the most important tools available to scientists for determining the three-dimensional solid-state structure of complex organic molecules, such as proteins, and for confirming the structure and composition of new chemical compounds.
Hi everyone, I'm Susanna, an undergrad chemistry student at East Tennessee State University. Today, we're going to be walking through an X-ray crystallography experiment. First, let's review a few basic chemistry concepts before we get started, especially the difference between ionic and covalent bonding. In the nucleus, we have positive protons and neutral neutrons. Around the nucleus, negatively charged electrons orbit the nucleus in orbitals. The outermost orbital is called the valence shell. The valence shell is full of 8 valence electrons. This is the most stable form of an atom with a full valence shell. However, most elements do not naturally have a full valence shell, so they will form bonds with other elements to stabilize. The two main types of bonds that we'll go over today are ionic and covalent. To review ionic bonding, let's look at an example. Here, I've drawn two elements. We have chlorine, and we have sodium. Chlorine has 7 electrons in its valence shell, and sodium only has 1. Therefore, neither of them have a full 8 electrons in their valence shell, and neither of them are stable. When they come into contact with each other, sodium's 1 electron in its valence shell will move over to the valence shell of chlorine. Therefore, they both now have 8 electrons in their valence shell and are stable. Since sodium lost an electron, it now has a positive charge, and it is called the cation. Since chlorine gained an electron, it now has a negative charge, and it's called an anion. Now, let's talk about a different kind of bonding called covalent bonding, and let's look at an example. Here, I've drawn two atoms of oxygen. Oxygen has 6 electrons in its valence shell. When two atoms of oxygen come together, they form O2, or oxygen gas. To do this, they need to bond together. These 4 electrons, 2 from each oxygen, are shared between the two atoms. This way, each atom has a full valence shell. Instead of actually losing or gaining electrons, they're shared between the two atoms. Therefore, we don't form any cations or anions, since neither atom is fully losing or gaining an electron. Today, our experiment will be focusing on pyrite. I have a big piece of pyrite right here. Let's talk a little bit about what makes up pyrite. Pyrite is made up of iron and sulfur. Iron has a 2+ charge, and sulfur has a -1 charge. Therefore, we need 2 sulfurs for each iron in the pyrite, making the chemical formula FeS2. Because of this, another name for pyrite is iron disulfide. Within the mineral, all of the irons and the sulfurs form a network of charges between each other because of their negative and positive charges. To learn a little bit more about the molecular structure of pyrite, let's go to the lab and see some X-ray crystallography in action and how it can help us learn some more.
Once in the X-ray crystallography lab, Susanna begins by removing some smaller fragments from a pyrite crystal purchased from a local gem and mineral shop. She places her petri dish on a microscope stage and brings it into focus. She's looking for a small crystal, no larger than 0.3 millimeters in diameter, as this is the sort of crystal that will diffract well. She's found a promising crystal. The next step is to mount it on the tip of a fiber that is transparent to X-rays. Here, she's using fishing line. Once the crystal is mounted, it's time to set up the experiment. At the console, she opens Chrysalis Pro, the software used to control the diffractometer, and then opens the diffractometer door. She carefully removes the crystal from the previous experiment and then loads her own. Now, it's time to center the crystal so that the X-ray beam passes directly through it. The crystal will rotate during data collection, so it is important to make sure the beam will pass directly through it at all angles. This process, shown here in time-lapse, should not be rushed and may take up to 20 minutes to complete. Once Susanna is confident that the crystal is centered, she sets the parameters for the pre-experiment. Once Susanna is confident the crystal is perfectly centered, she shuts the diffractometer door, presses the door lock button, and returns to the console. Susanna adds her name to a list of researchers so she can be identified with the experiment. She enters the formula for pyrite, FeS2. She enters the name of the compound, and then sets the exposure time for each X-ray frame. Data collection takes about 5 minutes. Areas of high X-ray density appear as spots, just as in the Bragg's early photographs. Once the pre-experiment is complete, a screen will appear that gives an estimate for how long a full experiment will take. It also provides data indicating the quality of the crystal. Pyrite is usually highly crystalline, so Crystallus Pro is giving us an estimate for an experiment time that's only 16 minutes long. Typical data collection times range from a few hours to a few days. It looks like Susanna has a great sample, so let's go ahead and start the experiment. Crystallus Pro will take a short movie of the crystal, shown here in time-lapse, and then the experiment will begin. As the experiment progresses, Crystallus Pro will attempt to determine the unit cell of the crystal, which is the smallest part of a crystal that, when repeated, shows the full pattern of the lattice. Next, Susanna returns to the desktop to open Crystallus RED, or reduction. Once Crystallus RED opens, Susanna selects her experiment from the list and proceeds to review her data. She is looking for round spots of roughly equal size, evenly spaced, as these are the attributes of a good data set. Next, she adds the beam stop mask, so the beam stop is not included in her data set. Finally, Susanna reduces her data, which is the last step in preparation for solving her data set. OLEX2 is the software Susanna will be using to solve her data set and is available either through Crystallus RED or from the desktop. Clicking the Solve button will generate a preliminary model, but in this case, since pyrite is so simple of a molecule, we're only seeing two atoms, an iron atom represented by the blue sphere, and a sulfur atom represented by the yellow sphere. After further refinements, gold spheres begin to appear. These represent electron density, so we already know that there's more here than those two atoms. Expanding the lattice by typing the word grow and hitting enter reveals a lot more of the lattice, plus a lot of electron density. Further refinements indicate that Susanna has an excellent data set. She removes the electron density by spinning the wheel on her mouse. And now it is possible to see that there are indeed two sulfur atoms for every iron atom in the lattice. Susanna expands the lattice again, making it even easier to see the mineral's highly ordered internal structure. The R1 and WR2 numbers in the upper right-hand corner of the screen, 2.44% and 6.49%, are below 5 and 15%, respectively, indicating that this model matches her data very closely. This image would make an excellent addition to her lab notebook and report, so she prints it out and asks her instructor to retrieve a copy for her.